as we look at acceleration and we look at this rule of thumb, if an object is slowing down, the acceleration is in the opposite direction of the motion. So I'm going to prove that using this equation. We talked about it with the graph and we talked about it with the rule, but I want to prove it with the actual equation here, okay? So let's do one quick problem. Let's say that I am moving in the negative direction. So let's say my initial velocity is negative 10. My final velocity is negative 2. And let's say I made that change in 4 seconds. Okay? So based on the rule of thumb, I'm going to be slowing down here, so my acceleration should be in what direction? Based on this rule of thumb, if I'm slowing down, moving in the negative direction, my acceleration should be positive, right? Based on the rule that we see here. But let's see if the math proves that. So do you remember what this sign right there means? It means change in, right? It's called delta, but it means change in. So it really means final minus initial. So when I go set up my acceleration, I'll go final velocity, negative 2, minus initial velocity over time. All right, so what happens here? When I have a negative, negative, it becomes a plus sign, which means I'm at plus 8 divided by 4, which means my acceleration is 2 meters per second squared. Right, 2 meters per second squared. So my acceleration does come out positive because I'm moving in the negative direction and I'm slowing down. So it's a little bit counterintuitive, and it has something to do with vector addition. And so that it gives us a little bit more of an explanation as to why my acceleration comes out positive, but we're not really going to dive into the vector stuff behind it. I just want you to kind of remember that rule of thumb so you can help check yourself as you do the math. Right? It's really easy to just do bigger minus smaller number when we plug it in, but it's always got to be final minus initial. Okay, just really careful with that. All right, so let's practice just a couple easy acceleration problems, and then we'll move into some more complex problems. So this is an equation that you can put on your equation sheet if you want. You don't have to if you don't want to. We're going to get a couple others today that do almost the same thing. Okay, let's try this one right here. Okay, Marissa's car is moving at a speed of negative 28.6. She slows down. What is her acceleration? So I think you guys can go ahead and do that one. All right, I like to start making my list. It's not a huge deal right now, but my initial velocity is negative 28.6. My final velocity is negative 24. My time is 3.2. So acceleration, I go negative 24 minus negative 28.6 over 3.2. And my acceleration should come out positive, right? We're slowing down in the negative direction. I had it at about 1.44 meters per second squared. Is that what you guys said? Okay. Do you remember where that unit comes from? Why did we talk about meters per second squared? Right? It comes from the fact that my velocity is measured in meters per second, and my time is measured in seconds. So when I do that math, my units have to do the same thing. So it's meters per second. Okay, but let's break it down a little bit more than that. What it means is that for every second that goes by, my object slows down 1.4 meters per second. Okay, so in this scenario, for every second that goes by, their velocity goes from 28.6 down to 27.2, down to 25.8, or whatever it happens to be, down to whatever, right? It slows down for every second that goes by. My velocity decreases, in this case, by 1.4 meters per second, right? So in acceleration, we need to really be able to think about what's happening, right? In every second that goes by, my acceleration changes by 1.4 meters per second, right? That's what we see there. Okay, any questions about that one? Okay. All right, velocity and acceleration tell us two very different things. Velocity tells us how fast or at what rate our position is changing, right? We moved 10 meters in 1 second. We moved, 4 meters in 1 second, whatever it is. But velocity tells us how fast our position is changing. Acceleration tells us how fast our velocity is changing. Okay, so it's a little bit different there. I'm not going to have you solve this problem, but if I'm looking at this one, 75 kilometers per hour in 5 seconds, what do you think the issue is here? Do we see a problem? Yeah, these units don't match, right? They don't match. Okay, so actually let's do this one together. This says I'm moving at 75 kilometers per hour and I come to a stop. So am I given a final velocity here? I'm not given a numerical value, but what do I know about this? My final velocity must be 0, right? So you don't have to write this one down, but let's see here. My initial velocity is 75. My final velocity is 0. My time is 5 seconds. This needs to be converted from kilometers per hour to meters per second. And so the shortcut to go from kilometers per hour to meters per second is what? Divide by 3.6, and I get 20.8 meters per second. Okay? So in this example, I'm moving in the positive direction and slowing down. So what sign should my acceleration have? Should it be positive or negative? It should be negative, right? So when I go to plug this in, I go final velocity. Acceleration equals final velocity minus initial over time. And I get negative 4.17 meters per second squared. Okay, it's really easy here to just go 75 or 20.8 minus 0, right? But you have to think about the fact it's final velocity minus initial. Really, really careful with that. Okay, questions about how we got to that? So that's basic acceleration. All right. Think about this for just a second. You don't have partners, but think about these questions for just a second. This question, I think I only give you one. Okay. Think about this one and see what you can come up with. No, you don't have a guess, or the answer is no? The answer is no. Okay. If the acceleration of non is 0, does it mean that the velocity is 0? The correct answer is no. That doesn't mean that. What would be the case in which that would be, like, no would be true? Like, what's an example that proves that's true? If the acceleration is 0, does that mean that my object is necessarily stopped? No. What does it mean? That I'm going the same constant velocity, right? I have cruise control set, right? That's what that means. So if my acceleration is 0, it does not mean that my velocity is 0. It just means that I'm not speeding up or slowing down. It means that my velocity is constant, right? That's something really important. Okay, now we're going to get in kind of the meat of what we want to do today, which is called kinematics. What does the prefix kina mean? Anyone have an idea? Kinetic, or kina means motion. Okay, so these are what are called kinematic equations for constant acceleration. But I'll just call them your kinematic equations, and I'm going to give you 3 big ones. Okay, these are called your kinematic equations. I would probably label that on your equation sheet as well. These are my kinematic equations, and I'm going to give you 3. Okay? Kinematic equations is what I'll label them. Okay? This is our first one right here. Don't worry about this for right now. This is the equation you want to write down. And that should go on your equation sheet as well as in your notes. This one go in your note on the equation sheet. This one I want to just talk through it for a second. So this is the one that we already knew, right? That's the very first one we got for acceleration. Do we agree? It's the very first one. But if I rearrange this equation, times t, that leaves me with TA equals VF minus VI, and I move VI over. This is the same equation, right? They do the same thing. VF equals VI plus AT, right? It does the exact same thing. So this equation that you already had and this equation that you currently have, they do exactly the same thing, right? It doesn't really make a difference which one you use. I lump this one in with our big three kinematics, so I use this one much more often, okay? When we use these equations, okay, there's going to be three of them, like I said. When we use these equations, it's super, super important that we know acceleration has to be constant. Whatever it is, it's got to be constant. So that means if we have a scenario that we saw like on our graphs, where we speed up for a while, and then we go constant, and then we slow down, and then we do something else, we can't solve all of that in one equation, right? Because the equations are for the time period in which the acceleration equals A, or whatever it is, right? We can't put in the speed up, then the slow down, then the stay constant. We can't put all of that into one equation. So these are just for the period of time where acceleration is constant, right? Then if we have another section of time where it's not, we do that section of time, and then we move forward. We won't get to problems like that for a little bit. But this equation is one of our big three. So we do need that one in our notes. Okay, we solve it exactly the same, okay? Why don't you go ahead and try this one on your own, because I think you'll know how to do that. The one thing that we need to be sure of here is that we look at that conversion, right? Kilometers per hour has to be converted. Okay, and I will just really recommend that you start making a list. My velocity initial equals this, velocity final equals whatever. It's asking for final velocity, so I like to put the question mark there. So I know this is what I'm looking for. Okay, that's up to you. All right, that's how we plug it in. Give me, what do you have for your final velocity? 32.1, something in that range? Okay, and then what's our units here? Just meters per second, good, because it's just velocity, right? It's not acceleration, so velocity is meters per second. Very good. Any questions about how we plug that in, why the numbers go the way where they do? Okay. Here is our second kinematics equation. They get a little bit more intense as we go. Right? Second kinematics equation. So go ahead and write this one down. Notes and equation sheet. Right? So what does the XF probably stand for? XF probably stands for final position or final displacement, right? This is final, we'll just call it position. Even though we know it means displacement, what would this be measured in? If we're talking about position, what would that be measured in? Distance or displacement, what would that be measured in? Meters, right? How far did we go, right? We talk about in meters. This is initial displacement. Initial displacement. So very, very often, most of the time, x sub I, initial displacement, can just be set to 0, since it's our starting location. So that means we don't care, when we're talking about these problems, we don't care what happened before, right? We don't care how we got to this like excerpt in time that we're talking about. We don't care how far we traveled before this. We just care about what happens for this amount of time, right? If that time is 2 seconds, I don't care what happened before the 2 seconds. I just care about that particular time, right? How far did I travel during those 2 seconds? So I don't care what happened to me before. Okay, so there's a couple different situations in physics where we get to kind of choose our frame of reference. So if it says, you start at 40 meters and you end at 80 meters, you can plug them in that way, or you can just say my initial is 0 and my final is 40, right? I can do the subtraction ahead of time. It doesn't make a difference. That's whatever you feel comfortable with, okay? VI, we know what VI is, initial velocity. This is time. This is acceleration, and this is t squared. It's important we know that only the t is squared there. It's not the whole term that's squared. It's just the t. That's super important. Okay, just the t that needs to be squared there. Okay. So what does this equation have that the first one didn't? It has x, right? It has position. And what did the first one have that this one doesn't? Final velocity, right? This is an equation that you can use if you're not given final velocity, right? There'll be problems in which you don't get every single variable. This would be the one that we'd use if we don't have final velocity. That wasn't given to us. All right, let's go ahead and try. I have a problem here that you can try with this one. Okay. Train accelerates from rest at a constant rate of 3.15 meters per second for 1.57 minutes. How far does it travel during this time? Okay, so let's go ahead and start picking out what our variables are. Okay, what's it mean when it says from rest? Yeah, and so what variable gets that 0? Okay, xi does get a 0, because we don't know what happened before that. Okay, but what else gets a 0? Vi, right? And my initial velocity was 0 because I started at rest. My acceleration is 3.15, and my time is 1.57 minutes, but I need to convert that. So how would I convert that to seconds? Do I divide by 60 or multiply by 60? Multiply. 94.2 seconds. And then it says, how far does it travel? Which means I'm solving for x, f. And that's my question mark. Okay. It's pretty important for me when I'm making my list, I don't put down extra variables. I only list what I have and what I need. There would be no reason for me to list VF here because it doesn't have anything to do with the problem. And I can solve without it. Okay? So, as I'm looking at my equation, I'm going to solve for XF. I know that XI is 0. VI is 0 times time, which is 94.2. Plus 1/2 times 3.15 times t squared. 94.2 squared. Okay, this whole term with initial velocity, that's 0, right? Do we need to bother plugging that into our calculator? This one, VI times time. VI is 0, so we don't need to bother plugging that in. So I'm going to go 0.5 times 3.15 times 94.2 squared. And I get XF equals 13975, or 76. Is that what you had? Yeah? So this is a big acceleration, right? We traveled a lot of meters in a relatively short amount of time, right? In a minute and a half. Okay. How did I know I needed to label it meters? Why did I label it meters? Right. We're looking for how far it travels. Last equation of our big three. When you write this one out, we could also just go 2a xf minus xi if that's more comfortable for you, right? Because that's what delta means, is final minus initial. So if that's more comfortable for you to write it that way, go ahead and do that. Right? But again, what do we usually know that xi is equal to? 0. It's usually 0. So for the most part, we're just going to go 2 times a times x. Right? We're usually not even going to have this. But if we do, we have to distribute that 2a through there. Okay? If we do, we have to distribute the 2a. Okay, so what is this one missing? This equation, what's it missing in comparison to the other two? It's missing time, right? It doesn't have time. So if you're given a problem and you don't have time, you don't need to solve for it. You can just use this equation, right? You can use this one. So, oops. Let's try one here. Go ahead and try this one on your own. Is that what we had? Make sure when we're looking at that distribution of x, right, this is just 0. So we can just drop that, and then we'll go 2 times 3.5 times xf, right? So sometimes I find that people want to, like, add those together, 7 plus xf. That's not true, right? It's multiplied. That whole thing is multiplied together. So when we get that term, to get this by itself, we have to divide that over. Okay? And that 0 squared, right, we can end up just dropping that out. So any questions about how we got to that one? Okay. Make your list, pick out your variables, and then see which equation you need. So this is not necessarily the last one. Okay? Write out what you got and write out what you need. Right? I like to use the question mark for showing me which one I need to solve for. All right, so do you have an answer for me? First of all, tell me what equation should we have used? Any ideas? Did this require more than one equation? Tell me the one thing that every equation has in it. Actually, there's two things that every equation has in it. It has initial velocity and it has what? Every equation has initial velocity and acceleration. Was acceleration given here? No. That means we have to solve for acceleration first, and then we can solve for time. So this one was a little bit tricky, right? Because it required two equations. So let's think, if I need to solve for acceleration first, but I don't have time, what equation must I use? The first, second, or third? The third, right? I need acceleration, but I don't have time. So I have to use the third equation first. Okay. So that means I would go final velocity squared equals initial velocity squared plus 2 times a times 125. Right? The 125 is my final displacement. My initial displacement is 0. Right? I don't have to plug anything in there. So as I do the math, I'm going to go 25 squared, 15 squared. So that's 625 equals 225 plus 250 times a. Agreed? So I'm going to do the subtraction. That gives me 400. Okay, let's look through this, right? First thing I need to do here is move over that 225, and I have to subtract that over. So 400 equals 250 times a, right? So 400 divided by 250 is 1.6 meters per second squared. And so now I need to solve for time, right? So once I have all the things I need, I can just go use my easy equation, my first one, to solve for time. Right? So I'm going to go up to the top here, and I'm going to use my first equation. So VF equals VI plus A times T. Right? And solve for a time that way. Right? But we had to recognize that, we weren't given acceleration, and that's in every equation, so we have to have it. right? So 10 divided by 1.6. My time equals 6.25 seconds, I think. Yeah.